Hey everybody. In this video, we're going to take a couple of examples of problems involving quantum numbers and try to unpack them and just do a little bit of a review on how we can assign quantum numbers to orbitals and what that all means. This is going to be kind of a long video, probably, so I'm going to break it up into sections here, and I just want to remind everyone that if you want to skip ahead and just take a look at a specific example, you can always do that in the table of contents. To start off with, I just want to review a little bit about orbitals and the definitions associated with them. So really, just to break things down and make it really simple, the main thing that I want us to think about when we think about orbitals in this introductory section is to think about them as just simply places where electrons inside an atom can live. So we're going to represent them on the slides here as just boxes that can contain certain numbers of electrons here. Specifically, an individual orbital is an area of space where up to 2 electrons can live. And I'm going to represent those with little arrows that I'm going to populate the boxes with here, and I'll explain why I'm doing that in a second. But we can have up to 2 electrons that are living in the same space at the same time in this model. And that's one of the things we need to keep in mind. The maximum occupancy for each of these orbitals is going to be 2 electrons per orbital. Okay, so generally speaking, that's the definition that will work for us as we're introducing these topics. And we're just going to learn a little bit more about how to organize them. And when you're thinking about where an electron is in an atom, and you want to know exactly sort of what area of space you might find it, you need to have some sort of addressing system for understanding which orbital you're talking about. So that's where the quantum numbers come in. And quantum numbers here, as I have on the slide, are sort of meant to signify an address for a particular kind of orbital that helps us kind of group them into categories that have a hierarchy to them. So there are 4 total quantum numbers that we're going to look at, and 3 of them relate to the orbitals specifically. And then there's a 4th one that is specifically related to an individual electron. So I'll get to that. But we are going to be looking at these quantum numbers individually here and trying to do a couple examples with them in this presentation. So just to review what they are, we have our principal quantum number, n, which tells us the energy level that we're in. The other name for an energy level that is often used here is a shell or an energy shell. And the reason we call it that is because as we increase the distance where these electrons are spending their time from the center of the atom, as we get further and further away from the atom, it's almost like we're adding layers to our picture of how that atom would look. And as we get further away, we're dealing with groups of orbitals that are sort of expanding further and further away from the atom. And so they almost look like layers or shells. This is going to be sort of the highest level of organization that we can put on orbitals. And we're going to kind of consider this to be the superfamily, or maybe just the family of orbitals that we're going to be working with. This is a large group that's all going to fall under one heading here. So this would be your sort of last line of your address where you're designating the general area where you're going to find something. And there's a lot of individual additional pieces of detail that we can add to this to get more specific. Okay. So if this is the family, we can split families of orbitals that are sort of organized by their energy, right, down into smaller and smaller subgroups. And the first group we split them into with quantum numbers is designated by the second quantum number, the angular momentum quantum number L. And this oftentimes is referred to as the letter that signifies which subshell you're in. So we're just within a family. You can get a little more specific. We are looking at an individual group within that family. And what that tells us overall is sort of the number that signifies is we're going to group orbitals in terms of the shape of those orbitals. So really what we get from the angular momentum quantum number here, the second piece of our address, is what group these orbitals fall into within their bigger family. We're going to organize them by the shape, the general shape that they have. Okay, so this is sort of a subgroup within those families. All right, and we'll divide those down. If we want to talk about an individual orbital that's within one of those little groups, we're going to use the third quantum number, the magnetic quantum number m sub L. And so this one is going to tell us the individual orbital that we're talking about, right? So if you want to talk about an orbital, you need at least 3 quantum numbers to specify exactly which one you're talking about. And in terms of what this tells us about the orbital and how it distinguishes it from other orbitals that we might find in that same family, it's not about the shape anymore, because that's already been broken down in our subshells. But instead, we're talking about maybe all these orbitals that belong to this subshell have the same shape, generally speaking, but they are going to have different orientations. And perhaps a bit later on, we're not going to treat the shape situation too much in this presentation, but when you actually look at a diagram of how these orbitals actually look in 3D space, that idea will make a little more sense. So we might return to that later. If you want an address for a specific orbital, you just need these 3 quantum numbers, right? The first one here tells you, generally speaking, how far away from the nucleus of the atom your electron density is going to be. As we increase the energy level, we are actually going up in energy as well. So that's sort of the region you're looking at. Looking at the specific group here is sort of analogous to looking at a specific neighborhood within that atom. And then if you want to look at a specific sort of street address for a pair of electrons, you'll have to look at that third quantum number, right? So we're getting more and more detailed as we move down this list. There is a 4th quantum number, the spin quantum number, m sub S. And this one is specifically for if you want to talk about an individual electron. So this would be the electrons themselves. Will have a specific indicator that will indicate which electron you're talking about if you have a pair of electrons inhabiting an orbital. All right, and this is sort of a unique quantum number because it can have values, and it can only have 2 values of +1/2 or -1/2. And what that indicates is something about the electronic spin, which is a property that electrons have. We don't need to go into it too much here. But actually, in my little diagram over on the left here, I was talking about identifying electrons and representing them as little arrows. And we could think about this electron on the left here having a spin of +1/2, because I drew the arrow pointing upwards. That means that its partner, the one that lives with it in that orbital, assuming that orbital is totally full, would need to have a spin of -1/2. All right, so whenever we have a pair of electrons that pair up and live together, they have to have opposite spin quantum numbers. All right, and so that gives each electron a unique set of 4 quantum numbers if we were going to use that to identify them. Along with this, there are some rules. And so I'm going to erase a little bit of my descriptions here. We'll try to keep those in mind as we go forward. And I need to just talk about what we're doing when we assign these addresses, because there's a numbering system that we have to keep in mind. And I'm going to write out the rules right now, and then I'll put them into practice in just a second. All right, so the rules for quantum numbers here are that the energy level, we're going to start numbering with energy level 1. And then if we're talking about orbitals that are in greater energy levels, we're just going to step up in the positive integers. We're going to go up by 1 each time, and each energy level is going to be labeled like that. It gets a little more complicated from here because, as we'll see on the next slide, there are some rules associated with these other quantum numbers that have to do with what energy level you're in, and then how many members of your little subfamily you have. So if you are numbering your energy levels, starting with 1 and counting up from there, the rule for L is that you can start with 0 when we're talking about L, and you can number up just like we did before, increasing by 1 each time. But the top number that you can get to, the highest number you can get to, is n minus 1. Right? And I'll show an example on the next slide, but to remind us sort of what this means, if you're in the first energy level here, right, just based on our rules, we know that the only value we can have for our address for our L quantum number is 0 here, because 0 is equal to 1 minus 1, right? Likewise, if you're in the second energy level and you are trying to figure out the possible values for L, right? If we just follow this logic, L could be 0 or L could be 1, but ultimately you got to stop there because 2 minus 1 is 1, right? So that's sort of how these rules work, and it's going to carry forward again when we look at M sub L, right? M sub L can have values of negative L, and we can increase by 1 going through this all the way up to a positive value for L. So I'll show some examples on the next slide of how that breaks down, right? But that's the rule. And then likewise, we already talked about this slightly here. This is sort of the extra quantum number that designates an individual electron. And that one is a little different because all we're trying to do is decide which of the 2 electrons that might live in an orbital we're talking about. And if we're talking about electrons and not just identifying an orbital, you have those 2 choices. It can be either spin up, which is +1/2, or spin down, which is -1/2. So this is what an atom essentially will look like if we're thinking of a single electron atom for starters. What I'm trying to represent here is that we already talked about with our principal quantum number, that as we increase n, we're stepping up from a lower energy level to a higher energy level. And I can draw kind of a progression here as we increase energy. We're moving from the bottom part of this figure to the top of this figure. And what we can see is that each family here has a different number of orbitals that live inside it, right? Or that are part of that group. So way down on the first energy level here, we can see just the way that I've drawn the diagram, this is what we find, is that there's actually just 1 orbital present in that first energy level, okay? And I'm actually gonna even designate a little bit further with this, that energy level here, again, we said can only have values of L equal to L equals 0. And so the subgroup that exists within that first energy level also just has 1 orbital inside it, right? And if I was getting really specific, I could talk about the individual orbital here, and M sub L here. Its possible values just consist of a 0 as well. So that would be the full address for that orbital that's living in the single orbital that's living in that first energy level. It has an N of 1, an L of 0, and an M sub L of 0 as well. All right, stepping up to the second energy level, I've got more options. So these energy levels get bigger as you start getting further and further away from the atom, not only in size, but also in just how many places there are to live in each of these families of orbitals here. So in this case, I actually have 2 subgroups that I'm going to draw here. And I've sort of divided them on the slide so we can see that. Once again, we have a region or a subgroup of orbitals where L equals 0, and that just consists of 1 member, right? According to our quantum number rules, M sub L here is also equal to 0. But the second group, the other one that I boxed off here, this is new to this second energy level. And this corresponds to a case where L is 1. Remember, with our rules regarding quantum numbers, this is allowed by our rules because n is 2 now, so L can be anything up to n minus 1, which means we have this extra group now that we can work with, right? And within that subshell, we have 3 different family members here. That corresponds to the 3 possible values for M sub L. M sub L can be -1, 0, or 1, based on those rules that we covered on the previous slide that we were looking at there. Okay. If we go up one more time, we can start to kind of see a pattern here. I'm going to end up with 3 subgroups. So 2 of them are similar to the ones that we covered on the lower energy levels, and one of them is new for this new energy level here. So again, we've got L equals 0, L equals 1, and this time our new one is L equals 2. And because L has a bigger value here, we also have more options for what M sub L can be. And according to our numbering scheme there, that helps us illustrate that in that subshell where L equals 2, we actually have 5 possibilities here, right? -2, -1, 0, 1, and 2, according to our rules for assigning quantum numbers. Again, the rules here exist just to help us remember that these different subshells have different numbers of orbitals, and the energy levels as well, stepping back a little bit, have different numbers of subshells in them as well. And generally speaking, you just get more and more possibilities as the energy increases here. So now I want to ask a question. I want to actually start solving some simple problems here. And this is just a set of problems that will help us try to understand how those orbitals break down and what we can conclude in terms of quantum numbers here as well. I've got a couple examples for different problems. So I have a question here that sounds maybe straightforward enough, but we need to figure out where to start. I just want to know how many electrons can fit into the third energy level. So I'm going to go ahead and try to break this down based on what we've learned already about quantum numbers, because that's one of the ways that we can come to a solution here, all right? For the third energy level, we know that N is going to be equal to 3, okay? And that's just by definition. We know N corresponds to the energy level. So the question is, how many total electrons can fit into that energy level? Well, we're going to have to come up with some possibilities here for L and for the subsequent quantum numbers as well. So L, we know in the second energy level, can have values of 0, 1, and 2, right? Because we can have everything up to n-1 for values of L. If we go back to our previous slide and take a look, we're in the third energy level up at the top of my diagram here, and we can see indeed there are 3 possibilities for L in the diagram we went through earlier. And then there will be multiple orbitals potentially that live inside each of those subgroups. All right, so that's the next thing to figure out. If you have an L of 0, 1, or 2, that's possible. We're thinking about M sub L now. Well, in this case, with L equal to 0, M sub L only has one value that it can be, right? Which is 0. So that tells me that there's one orbital that lives in that subshell. For L equals 1, we actually have 3 possibilities. Again, similar thing was illustrated on that previous slide, where we have M sub L equal to -1, 0, or +1. That tells me that in that subfamily of orbitals, we have 3 members, right? And then I have L value equal to 2 in my last possibility, and I'm actually going to end up with 5 possibilities here. M sub L can equal any of these numbers, anywhere from -2 to +2. All right. So if I go back to my diagram, I can see that on the slide as well. If I look at my third energy level, it looks like I've got 1 + 3 + 5. That gives me a total of 9 orbitals, right? So going back here, the question is how many electrons can fit into that third energy level? And what I've identified so far is how many orbitals I have to work with. I've got 1 here and a set of 3 in this subshell, and I've got a set of 5 in this final subshell here. So we pretty much have all the information we need to solve this. The only other thing that we need to remember is that for each orbital, you can store a maximum of 2 electrons. So if I'm trying to figure out how many I can fit total, I have 9 total orbitals present in this energy level. And that means that I can fit a total of 9 times 2, which is 18 electrons before that energy level is completely full. All right. And that would be our answer there. I have a couple of other questions to go through, but before we go any further, I have to indicate one more thing for us, which is that in addition to having a quantum number that identifies these subgroups here that we've put on the slide where L is different values, we also have sort of a letter that we can assign to each of these subgroups to tell us sort of something else about the shape of these orbitals, right? We could just use the quantum numbers, but it's a general practice to use letters as well to talk about these subgroups. And so I need to identify those. And the letters that we're going to use for L equals 0 here, which is an option for all three of these energy levels, right? We have a subgroup on each of these energy levels so far where L equals 0. That letter that we're going to define for that subgroup here is S. So we talk about S orbitals being orbitals that live in the subshell where L equals 0 in terms of our quantum numbers. So we have an S subshell here in the second energy level as well, and an S subshell here in the third energy level too. All right. So this is one subgroup that we can identify. When L equals 1, so that's also present on my second energy level here for the first time. These are orbitals that we refer to as p orbitals. This is the p subshell, because those have a specific shape, and in addition to the quantum number, we're also giving them a letter here from now on. All right, so we have a p subshell that is present in our second energy level for the first time, and we also have one in the third energy level. And then finally, for L equals 2, we have a D designation that we'll give to the orbitals that live there. So we have a D subshell for the first time in our third energy level, and that's the only one that we've got on the diagram so far. But subsequent energy levels after that will also have D subshells as well, and we'll keep adding to the total. There's also a series of F orbitals, which would come later. If we were to go up one more energy level, we would run into a situation where L could equal 3, and that's where you see the F orbitals. All right, but we'll treat these first 3 for starters. So now I want to ask a question here that relates to those lettering conventions. We are going to just ask a similar question, but now we want to know how many electrons can fit into the 3p subshell. So let's figure out what we mean by that. N here has to equal 3, just like it did in my first example problem, because the 3 in this name for the subshell corresponds to the energy level. So we just read that right out of our designation here. We also know what L needs to be when we're trying to figure this out, and that comes from the letter that we're given in the problem. If we flip back, I mentioned on our previous discussion here that we are looking at the P subshell when L equals 1, right? That's what we had labeled on my diagram here from before. So if we hop back to our problem, for a P subshell, L equals 1, right? And to remind everybody, S is where L equals 0. Those are S orbitals, or the S subshell. P corresponds to a case where L equals 1, and D is the subshell where L equals 2, right? Okay, so this is the location we're talking about. We're talking about a specific subgroup within the family of orbitals that exists at the third energy level. And we got to figure out how many electrons can fit there. So once again, we're going to figure out how many orbitals there are, and determining values for M sub L will help us with that. All right. We can see here that we actually have 3 possibilities for M sub L. We can have -1, 0, or 1. That tells us that within this subshell, we have 3 total orbitals, right? That's all we're trying to get at here. And to finish our calculation, if we have 3 orbitals present in that subshell, each orbital can fit a total of 2 electrons, which means that we're going to have a total of 6 electrons that can fit inside that subshell. All right, that would be our final answer here. All right, next we have a slightly different problem. We're not really asked about electrons this time, but we are being asked about all possible quantum numbers for electrons in the 2s subshell. All right, similar kind of question. It's just asking for something slightly different. So all we need to do is break this down again. Let's recall that n is going to be equal to 2 because we're in the second energy level, and that's part of the name of the subshell. And then L, because we have an S for our subshell designation here, we know L has to be 0. All right. That also means that if we're thinking about possibilities for M sub L, we only really have one choice. M sub L can only be 0 in this case, due to our rules for quantum numbers here. And likewise, we're now gonna break it down and figure out how many electrons are present, right? What we've learned so far is that we have a single orbital that's present in that subshell. So one orbital should give us 2 total electrons that can fit there in that subshell. But what we were asked for was all the possible quantum numbers for the electrons that live there. So really all we have to do at this point is note that n can only have one value, right? N is 2 here. L can only have one value, 0. M sub L can also only have one value. M sub S, again, has 2 possibilities based on the specific electron that's living in that orbital that you're talking about. So if I was going to write out all 4 quantum numbers and list all the possibilities, that would be my final conclusion here. You have 2 possibilities for M sub S, and all the rest only have 1 possibility for each of them. One final thing I want to say about energy levels in general is that the picture that I showed at the beginning, where we were first diagramming out the different orbitals, sort of had energy going up on the vertical direction in the page, and I was grouping the orbitals by their energy levels. It turns out that this is an accurate picture of what orbitals look like when you only have 1 electron in your atom. So say you're dealing with a hydrogen atom or some ion that only has 1 electron present in its electron cloud. The way that would break down is that you actually would have a distribution like this, where the quantum number n is the only thing that determines what or how much energy your electron is going to have. We can excite that electron and it can jump up to the second energy level, but it basically has a choice between any of these places to live once it has that amount of energy, because all of those orbitals have the same energy. And if we excited it even more and popped it up into the third energy level here, all of these orbitals up on top here would be choices for where it would go, and there would be no difference essentially between where that electron could choose to live based on energy, right? One of the principles we started to discuss in this unit and we're going to be working with is the fact that it's just generally a law of nature that that electrons and atoms in general like to try to relax down to a lower energy level if possible. The lowest possible energy level is going to be the one that's occupied first, and then if there's no more room there, then we're going to start to fill up from the bottom to the top. All right. And so in a situation like this, it looks like the only thing we need to choose from is which energy level to go into. And after we fill up the first energy level, we start filling up space in n equals 2 and then n equals 3. Turns out things get a little more tricky when we start dealing with multi-electron atoms, because like we've talked about, there are different subfamilies of orbitals here, and we haven't looked at the shapes of those in this video, but each of these has a different shape. The s orbitals have a particular shape to them, the p orbitals have a particular shape to them, and the way that these orbitals start to overlap after they become occupied with electrons, that's actually going to start to affect how they experience their interaction with the nucleus, and that's going to change their energy a little bit. So for a single electron atom, this is the landscape that we'd be looking at for energy. And all you really need to know to calculate the energy of an electron is what the principal quantum number is, right? That's the only thing that's separating these different levels from each other. But in a multi-electron atom, where things are starting to overlap and the different shapes of the orbitals are starting to affect each other differently, we're going to actually get a little bit of a different picture. And each of these subgroups is going to start to sort of break apart from each other when we're trying to designate the energy levels here. So again, if I draw an energy level axis here, energy is increasing as we go up the page. We have s orbitals and p orbitals, right? And d orbitals as well in this third energy level. And actually, they're going to start to be offset from each other when we look at the energy landscape. Turns out that this family of p orbitals here is actually going to be a little higher in energy than the s orbitals. And the same thing is going to happen up here. Our p orbitals are going to be up a little bit from the s orbitals, and our d orbitals here are up even a little further still. So if we're just considering the first three energy levels, we actually start to see a little more of a stepped pattern here, right? So if I have electrons that are trying to fill up this diagram, I'm going to fill up the very bottom layer first, this s orbital down here, and I'm going to fill that up with electrons. But say I run out of room there and I need to start filling up the diagram even more. Well, now I actually have a choice between the s and the p orbitals, and I'm going to fill up s all the way before I start filling up p, and I'll get everything in there. And after all of those electrons are slots are filled, after all those orbitals are full, then I'm going to move on to the s orbital here, and then the p orbital here, and so on, right? And this can actually get kind of tricky as we go up in energy levels. I'm not going to fill up the d orbital quite yet because it turns out that things will start to overlap even a little more beyond this. But it's just important to know that in terms of calculating and understanding what energy your electrons have in the atom, if you're dealing with a single electron atom, n is the only thing you need. So this is the only quantum number needed to determine what it is that we're looking at for the energy of our electrons. Here, we actually have to know two things. We have to know the energy level, and we have to know the shape of the orbitals, or in other words, the subshell that they're in. All right. So I think that's where we're going to leave it today. This provides a little bit of an introduction to orbitals without even looking at the different shapes that they have, but it does introduce us to quantum numbers and how to use them. So that's where I'm going to leave it for now. Thanks for watching, and I'll see you in the next one.